likelihood estimation, maximum likelihood estimation, which we're going to do both theoretically a couple of times, and then we're going to run some code using another sports example. So that's where we're going. You should be able to find everything on the course page. So if you scroll down, one of the reasons I create a course page for my classes these days is, I think most people don't like Duo Mobile. You can just access my website directly without having to log in. If you're not pinning it to your browser for the next month and 4 days, what are you doing? So what we've done so far this semester, we started working with numerical methods, which was essentially the big idea there was just, we instead of taking derivatives using analytical methods where we essentially use a limit as the epsilon goes to infinitely small, we are approximating that with very small differences. So our delta is very small. And that really opens up a whole world for us, so long as we have computers. We could do this by hand, but it's just incredibly time intensive. We did simulation. Looks like I forgot to post our first nonlinear least squares regression video from last time. So if you weren't here, hopefully you were able to find that on the YouTube page. If you didn't, that's also fine. If I ever forget, you can just click on one of the videos that is posted, find my channel, and then just go to the live ones. And notice the view count to be about 4. Because I haven't been, like, subscribe, leave your questions and comments in the chat below.
How many views do you need to monetize it?
So it's not per video. I actually do know the answer to this, and I'm nowhere near it. People apparently don't care too much about nonlinear least squares. It has to do with subscriber count, so you have to get like over 1,000, and then something like, like 3,000 views in the last year or something, which is like not, like in the scheme of things, not that large a number. But I am nowhere near it. Okay, so we're going to pick up here. We've done the first part, and we're just continuing with the second. So I just want to walk you through a bit of what we did last class, which I know starting a class with exactly what we covered last time is not the most... what's the word, like, can't even find the right word, so that's auspicious. So what we did last class was, I'm not even going to try. We started by thinking about nonlinear least squares. So this is essentially, what we've done so far, like in all of econometrics, is think about, this type of function where we have a bunch of betas, we multiply that by the data, and then we're trying to estimate some function that looks like this. So, we have some function, our ordinary least squares is some function. We're trying to predict y using some function which takes in some data set x given our parameter set beta. So our equations look like this, and then we have some error term here. And in OLS, this function specifically has been it's been linear. So it's, we have our beta 0, which is, we're multiplying this times 1s. So this is just, we're treating 1 as our data. And then we have beta 1 times our x1 plus our beta 2 times our x2, and so on until we have our error term. And these are the kinds of functions that we try to minimize in OLS. It's a very general class of problems. We can treat x2 as like a square term. We can do this with polynomial terms, which allows us to include some curvature, even though this is a linear model. So it's a very flexible class of problems. What we did in nonlinear least squares was extend this a little bit further. So we said, what if we could actually do something that's different than this? There are some functions that we can approximate with a linear model like this, but the actual like parametric form is very tricky to set up in this kind of way. So we walked through an example last time where we said nonlinear least squares. Sometimes I feel like it should be NLLS. Last time we said we're actually going to make this more flexible. So instead of thinking of f as this linear function, we're actually just going to leave it a little bit more generic. So we're going to say our goal is to minimize our mean squared error, but it's going to be of different functional forms. So it's not going to take this functional form directly. But our goal still is to minimize the mean squared error, or mean squared residual. So we want to minimize this thing, where we take each observation. So we're going to look over each observation. We're going to then square the difference between the observation and what the function tells us. So this is, we're essentially just rearranging this thing and then minimizing the error. So this is just our data and then our parameter set. So we're going to take the difference and then we're going to square it. Sometimes we write this in just the sum of squared residuals or sum of squared errors. Sometimes we normalize this by the number of things we're adding up. Either way you do it in general, as long as the n is constant, they're going to give you the same answer. But we can write this also as, this is just rearranging using this equation. So this is the objective function, so the thing we're trying to minimize. With OLS, we can just do this analytically. We can just minimize the mean squared error analytically of these kinds of functions. First derivative, first order conditions, you've seen all of that before. And you've probably even proven some of those results in your econometrics classes. Turns out when we have more complicated functions, that kind of minimization approach is not tractable. There are lots of functions like this where actually trying to solve the first order conditions for some function of parameters is just not going to be solvable with pen and paper. So what we did is we took our numerical methods and applied them to this context. So we have some function. We're trying to use that function to predict our values, our outcome variables, using that function. And the goal was just we want to use our mean squared error as our objective function. And then we're just going to think about like Newton-Raphson or like similar kinds of methods to try to find whatever the betas are. So that's what we set up last class. What we were doing is essentially relaxing one of the assumptions of OLS, which is this linearity. So the function is linear in the parameters, which is really, really nice for tractability reasons. What we're going to pick up with at the beginning of class today is relaxing a different assumption, which is this one. We're going to change the objective function. Instead of saying we're going to minimize the sum of squared errors, so where we take the square of the difference between the objective and the function itself, and try to minimize this thing using the betas. What we're going to do instead is use an absolute deviation as our objective function. This means it's really hard to take derivatives. We like this one because we can take derivatives, and then everything in OLS just kind of falls out really nicely. But what we've been doing is building up the tool set to not necessarily need an analytical solution. So this puts us in a world where we can actually try to change the objective function to suit our needs. So this is the first relaxation we talked about in this notebook. This is going to be the second one. We're going to do one and then the other. We're not going to do both at the same time. Although in theory, that's something you could definitely do. So we could do nonlinear least squares, but we'd have to call it something else. Least squares comes from the objective function, but you could, in theory, think about more general functions and then think about a different objective function that would be totally reasonable, although maybe a little more challenging. But I think after today, all of this should be pretty clear. Let's see. So that's where we're going. So for the first part of class, we're going to focus on quantile regression, just doing this relaxation of the objective function into other forms. And then the second half, we're going to talk about maximum likelihood estimation. And then if we have time, we'll make it to an actual problem. Any questions before we get in? This is my big pitch for the day. This is where we're going. Any housekeeping I'm forgetting about? So if you, I guess one thing, if you are still working on the checkpoint, I'm going to be in my office. I have a thing right after class until 1 o'clock. So I'll be back in my office maybe a little after 1. And then I'm going to be around all afternoon until maybe, I might be out of the office around 3:30. So I think a target time to show up would be like 1 to 3 if you have questions about the checkpoint. My goal with these checkpoints is for you to not feel like this is basically like homework, but I think a little more structured. So I really hope that you're not doing this on your own. So I want to see you in my office. These are things to talk about. So come and say hi. I don't have snacks in my office at the moment, but you can come say hello to my plants. Okay, so that's where we're going. So what we did last time was set up nonlinear least squares. This was the thing, I've written a lot of this on the board already, but there's a lot more to talk about here, and we talked about this in class last time. But it's one of the nice things about the linearity is that we can do these kind of expectations, right? So it's we just plug in the value. The expectation of y given x is just the function itself. But when we extend our functional form into other types of functions, like the one I showed you last time, things get a little more complicated and our analytical solutions are less than tractable. So this was just a picture of Twitter data. So, we have generally with growth curves, like with Twitter or with cells in a petri dish, it sort of has this exponential, what's this called? The function is ReLU, logistic. So we have this logistic growth curve. So the alpha tells us, where the peak is, and then the other parameters tell us both the starting point on the vertical axis and then how quickly it converges. So we walked through this whole thing. This was the objective function. by plugging in the logistic in for f. And then our goal with this exercise was to estimate the betas. So we're still going to call the betas beta, the parameters beta, but it's just a vector, and we've called these alpha, delta, and lambda, or gamma. So then we talked through, the starting values, how we would guess them using the data, and then we walked through and actually fit this thing. I think this is an amazing picture. We have this, relationship through time on the horizontal axis with our data, and it turns out the logistic curve matches this really nicely. We talked through a couple of alternatives after, I guess, we walked through getting the variance covariance matrix for inference. But we talked about extrapolation. This is I think one of the motivating pictures. This is the in-sample fit for, we had a cubic polynomial. So this is like time squared, time cubed. And then we also had the nonlinear least squares model. Both of them look really nice on the domain of the model, but then out of sample, they seem to fall apart. We also walked through the Snapchat example where, I would expect Snapchat to follow a logistic growth curve, but the data we have is like Snapchat's growth sort of took longer. And the data we have is on a smaller interval where we can't, like in the data set, we don't have the ability to sort of like pick up the curvature in the logistic function. So this is one example of what we call the identification problem, where there are lots of separate models that could explain the data. You may have heard identification in the context of like, establishing causality. We often talk about it in that context. The problem of causality is just that there are multiple models that could explain the data. The same is happening here. We're just thinking about the identification problem as multiple parameter values that could explain the data. And here, because we don't see the curvature, we don't know where the upper and lower bounds are. So when we actually ran this, we ended up seeing that we didn't get convergence. So we ran this a bunch of times, and you can see each time we ran it, one after the other, using the previous round as the sort of initial guess, the starting point for the estimation. You can see each one got slightly different, and it looks like it's flattening out. So that was the lesson. Like, we need to be careful. We need to make sure that our data can support the model and the parameter values that we're using. And if we get it wrong, there's sort of like more upside and more risk to using nonlinear least squares. The upside is your model can just be like a better fit. You're imposing additional structure on your data. But if your structure is wrong, then that really leads to some serious mistakes. Or maybe not mistakes, but errors. And not everything needed least squares, nonlinear least squares. You're familiar with the Cobb-Douglas. It's like a production function. You can use it as a utility function. It looks like this. This is nonlinear, but some functional forms like this can actually be linearized. So one thing we often do with the Cobb-Douglas is just take the log. Some of you solved, production functions and utility functions, like those maximization problems in like your intermediate class. You solve them using the log, which can be nice. And what you see here is we can actually turn this this nonlinear function into something that is linear. So this is definitely linear. It's just what we call log linear. So we have, instead of trying to estimate y, we just estimate log y. Our intercept term is just the log of the beta. So if we want to get beta and we run this model, we just have to take our estimated value to the exponent. So we raise it to the exponential. And then here it's just we're going to use, instead of C as a predictor, we're going to use log C. And then our beta is just gamma. And then so on. So this is actually a really nice application of OLS. And part of the reason Cobb-Douglas is so useful. Okay. You have to think about the error terms when you do this, but this is something we like to do. Any questions about that? So nice theory, good example, and bad example. So the next thing we're going to do is talk about quantile regression, which is with nonlinear least squares, we relaxed the linearity assumption. So this is linearity. And then for quantile regression, what we're doing is we're relaxing the error term, the sum of squared error terms. So this is the original OLS, the least squares error term. What we're doing instead is introducing an absolute deviation error. So let me just walk you through what we're about to do and how to set it up. Can you all read this, or is this too small? It's fine? Okay. It says smaller text than I usually use in slides, but I guess we can zoom in. Okay. So nice. So nonlinear least squares, we relaxed one of the assumptions, but we were still estimating the conditional mean. What we're doing in quantile regression is we're going back to a linear function. So we're going to use this kind of function, but we're going to use a different objective function. So instead of asking, what the expected value of y is given x, we ask something about the quantiles. One of them is the median, which for some applications, thinking about the median is the right objective. So instead of thinking about like the mean, which is often what we think about, one example is with house values. One of the nice things about the mean is it's very easy to compute. Mathematically, it's very nice. We can take derivatives. There's no real problems mathematically with the mean. But one of the okay, I just said there's no problems with the mean. Mathematically, it's very nice, is my point. One of the problems with the mean is that it's very responsive to outliers. If you move, like if Jeff Bezos moves in, everything, like the mean moves up by a lot, which in some cases is fine, but in some cases is not what we're looking for. So when we're thinking about like house values, often we try to estimate using, we often estimate with means. It's at least something that can be useful. We don't always do it this way. So when we're thinking about these kinds of things, sometimes it's just nice to use quantiles. So let's just talk about the first kind of quantile. I think that's maybe easiest to think through, which is measuring the center point of the data, but in a different way. So our original loss function from OLS looks like this, where we're just taking the error, we're squaring it, and then we're trying to minimize the error. So it looks like this. To get the median, actually, we can just take the absolute loss. So the only difference between these two things is instead of using the squared to turn all errors into positive numbers, we're just going to take the absolute value. I'll show you a picture of this in a second, but the main idea is we need some way of measuring deviations on both sides. So if you overestimate and underestimate, we want to treat these both as errors and both as like positive numbers. The squared is nice mathematically. It treats both sides equally. The absolute deviation is another way of handling this normalization of errors onto the positive reals. And it turns out when we do it this way, we get the median. The mean is just sort of a product of this particular loss function. So this is just a visualization of the two things. So in yellow, is this yellow? It looks more yellow on this screen. So in yellow, this is the absolute deviation. So on the vertical axis, I have the loss, and then on the horizontal axis, I have the error. So the larger the error in both directions, the higher the loss. So loss still goes up as we move away from zero error. So if we're predicting perfectly, we get an error of 0, and then if we predict in any way imperfectly, we get positive loss. And it goes up. So the further away we get, the higher the loss. With the absolute deviation, it's linear on both sides. We just have this this bend, this kick point at 0. With the square deviation, it's just this parabola. And what this does is relative to the squared loss, the absolute deviation, you can see it's not weighting the outliers nearly as heavily. Okay, and it turns out when we do this, we would get the medians. So here we get the means, and this one gives us the medians. And just to think about why this is true, it sort of boils down to the error. Why we get the mean in one case and why we get the median in the other. And this intuition, this is the big idea, I think, with quantile regression, is how we end up getting the medians. So I think if you can get this part, the rest of what we do with quantile regression is going to be very clear. So if you have limited attention budget, which I do in a classroom, this is, I think, the part to pay attention to. And then we're going to get into the weeds with the rest. So this is just I think a weird little animation. I got this from Alistair, who used to teach this class. Don't tell him, but I don't love this animation, but it's like good enough, I think, to communicate the idea. We just have 3 data points. This on the side here is intended to show the size of the error. We're at perfect when we've minimized our mean squared error when this little rectangle is 0. So what we're doing is just trying to pick our parameter value of mu, so a measure of the mean. And what you can see is as we get further away from the middle, the error sort of grows, but not linearly. So what this means is we sort of have to do this balancing act, where when we pull in this direction, we're being very influenced by the values that are very far from 0, and we're being influenced only a little bit when we're close to 0. So this data point here near 0 is contributing almost nothing, while the 2 data points on the edges are contributing most of the loss. And your intuition is like, at least when I see this picture, I think, it's really hard to know exactly where the middle is. And that's because this is quadratic. It's like, it's not a linear function. But you can see roughly the balance is when these two are about the same height. This one moving farther away sort of pulls it closer. Like this one, at least in theory, should be a little closer to 0 than this one, just because this data point is closer to the third one. But this is kind of the intuition, right? Like the outliers are doing most of the work, and the middle values are doing much less of it. So this is the idea with the squared error. But what we're going to use for quantile regression is something slightly different. So here I have 3 data points. This is the OLS. So just we walk through and we try to minimize mu. So you know, for each value, each data point, we're taking the difference and then squaring it. It doesn't matter the order here because we're squaring. And then all we have to do is go through and take a first derivative, use our first order condition, and then solve for mu. So we can do this just directly. And you can verify that this actually is the mean. You could plug all those numbers in into a mean and calculate that. For least absolute deviation, what we're trying to do is minimize the absolute deviation from the mean, or from our parameter value. We're just going to take each value, subtract off our parameter, and then add all these things up, and then try to minimize. We can't really, you can do calculus on this. It's just a little more complicated, so I don't have that in the notes. But what happens here is you can actually minimize this thing using the median directly. The median in this case is the middle of the values. So, so the middle value in this case is 2/5. Okay, and why is this true? Why does this intuitively give us the median? Well, I have Alistair's second picture here. So for the first one, we walked through minimizing the mean squared error in blue. And what we found is the outliers have a disproportionate effect. And the middle values are not that important for where we pick our parameter value. So the loss comes mostly from the edges. But for absolute deviation, moving slightly in either direction changes the impact of the outliers by nothing. The two outliers are, as we move them back and forth, are not changing their total impact. You can see this. If we move slightly to one side, we increase this one, so that the error coming from this dot is going up by some amount, but it's going down by exactly the same amount from the other data point. So as we move this way, one data point is contributing a higher loss, but the other is perfectly offsetting it. So the outliers, as we move them around, are not sort of changing their total contribution to the loss. This is the key point. The last idea here is, if moving the two outliers around doesn't change their total loss, how do we pick the middle? How do we minimize the absolute deviation? We do that by picking this data point to be exactly at 0. So we want the loss from the middle one to be exactly at 0. Any questions here? This is the idea. Yeah, wait.
So like if we're working with a data set, are we just like, we're just gonna just plug in 0, or would we try to find the point that's closest?
Yeah, so maybe I'll step back to answer your question. what we're doing, so this is the error terms. This is the difference between the data point and our parameter value. So we're moving our parameter value around, and we're trying to pick, so instead of thinking about moving the data, what we're actually doing here is moving the parameter, which changes the error. So if we move the parameter closer to the upper values, then it shifts the upper values error closer to 0, and vice versa.
Yeah.
Does that answer your question? So then how do we pick the parameter that puts this middle point exactly at 0? The median. And the reason this is true is because both sides are contributing the same impact. We shifted in one direction. All of the points on this side, if we shift it this way, are lowering their loss by exactly the same amount as the points on this side are increasing their loss. And that's because it's linear on both sides. So all we're trying to do is just pick the point that puts the middle point exactly at 0 loss. Okay, I think if you get this, you get the rest of class. Any questions here? All right, both sides are contributing linearly. So moving in either direction doesn't change the total impact of the non-medians. Okay, so this is true when we have an absolute deviation. Both sides are the same slope, but there's an incredibly clever idea which said, what if we actually don't treat the two sides as having equal slope? What if one side had a slightly different slope than the other? So if we estimate a linear function, we estimate this using absolute deviation, then our parameter values are going to pick the medians for this reason. So you have to sort of change up your intuition about what the betas are doing. Using the absolute deviation, we get betas that are medians instead of means. But we can do this for lots of other quantiles. So this is the least absolute deviation giving us the mean. But what we can do is change the slopes. And imagine what happens if we changed the slope. Let's say the right side was much, much steeper. All of that intuitive work we just walked through, thinking through what happens when we shift in either direction, where one side perfectly offsets the other. Now that's sort of different. It doesn't perfectly offset the other. One side contributes 3 times as much as the other, if we're making it 3 times as steep. I'm going to show you a picture of this in a second, but think about what would happen to how we pick our parameter value in that case. Okay, so if we were to make the left side 3 times steeper than the right, essentially we would have 3 times more values on the right side than we would on the left. The reason we pick the median is because each side is sort of perfectly balanced. We want both sides to be balanced. When they're linear and the same slope, then we pick equal points on both sides. But if we change the slope, we change how many points on each side to make them balanced. So this is just another picture. So what I've done here, I think I might have explained this sort of backwards just a second ago. But this is a picture. We have, as you can see, I have a picture. And it's animated. On one side, we have a slope that's 3 times steeper than the other. To make them balanced, we want 3 times as many data points on this side as on this side. So just like before, when we were moving in one direction versus the other. Increasing in one direction perfectly offset everything in the other direction. Where we ended up is when we had both sides sort of equally balanced. So sort of, you can think of it both in terms of like balancing the actual like size of the data points on both sides, but in reality, the way we pick them is by thinking about the shifts. So you shift in one direction, how does that impact the loss? And we just want that movement to be perfectly balanced. When one side is 3 times steeper, we want 1/3 the data points as the other. So it doesn't really matter what the slopes are, it's just the relative slopes. So here, this is just a picture. We have, 5 data points. We have 1 data point on one side. We have 3 data points on the other. And we pick the second right at the middle point. So this whole idea of picking one of them exactly at the kink point, it still applies here. It's just all of the other data points, we need them to be balanced according to the slopes. Any questions here? Yeah, Wei.
So like, one of the other points focuses about median.
So this one
Yeah, like that. Yeah, that
or
one.
this one?
Yeah. Just kind of thinking about that. Does that change anything like at that point, or?
Yeah, so if we were to move this one to the 0, is that your question?
Yeah. Yes.
Yeah, so if we did that, then we would not be balanced, right? We would have 2 on one side and then 2 on the other. So it would be balanced if the slopes were equal. But here, because one slope is steeper than the other, then we have the 1 data point on this side contributing 3 times, and then sort of balancing with the 3 data points on the other. Maybe I'm not understanding your question.
Yeah, I think just because like as it's moving back and forth, that point gets like really close to the meeting. So that
Yeah.
means like we're going from being unbalanced to balanced in this animation.
Yeah, so it's like if we were to stop with this data point, if we were to stop right there, we'd be balanced in one way where we have equal on both sides. But in that case, this side would be contributing 3 times the loss that the other side would, at least marginally, right? It's like the thinking about the movements in the error. In that case, we could actually, like, think about it. So if we have 2 data points on one side, 2 data points on the other, and 1 at the median, we can actually reduce our loss by moving this direction. We're trading off loss coming from the 2, I can't think left and right now. It's too confusing. We're trading off the 3 times loss on this side for the 1 times loss on this side, which is a good trade for us. So how do we pick? Well, we want to move as far as we can this way, without moving. So we want sort of like a balance: 3 times the one, 1 times the other, and we need them to be exactly balanced if we can. Does that answer your question? Any others? That was good. Okay. So this is the general idea. As we move from the squared error to absolute deviation, we can sort of unbalance we can use asymmetric loss functions like this to give us any quantile we want. So this is the way we'll capture the loss. So if the error term is positive, we're going to multiply the error times tau. Tau is just going to be our loss, or sorry, target percentile, and then U is just the error. And then we're going to have 1 minus tau for errors that are on the other side. Okay, so then so the error, if the error is negative, we need all the errors to be positive in their loss. So because U is negative, we multiply this by a negative value, but then we just want it to be sort of the remainder of the error of the slope. So this is if this is 50, then this is also 50. If this is 75, then if we're targeting a 75th percentile, then 1 minus tau is going to be 25. So we sort of use this to balance the two sides so that we get exactly our target percentile. Okay. Any questions here? This is the implementation of that intuition we just developed with the balancing and then picking the middle. What we're going to do is actually use a linear model. So we have y is equal to the sum of the betas times the data. So it's basically just this thing. We're just swapping out the error. Okay, and this is nice. I think this is a useful way of setting up our model sometimes. In practice, I've actually never used this in my research. I know some people do, and we include it in the curriculum because it's one of those core advanced models. But you have to think carefully about when you would want to use this. It's applications where we care to not include a disproportionate effect from outliers. But it's useful enough that stats models actually has a quantile regression. So what I'm going to do is load this data set. This is house values from Pittsburgh. So I just have a ton of housing prices and lots of predictors. So you can explore this data set as you'd like. I have another class that uses data, and I've had lots of students use this for class projects. But you can play around with this. So columns, you can see the kinds of information we have at our disposal. So parcel ID, property house number. So these are just information about the location, so property address. But then we also have city and state. This is zip code. So if you're interested in differences between zip codes, you can use this. People care about school district. Have I told you I have a child? 5 years ago, I could have cared less about school districts, and now that's weirdly on my radar. Where you are in the municipality, the date of sale, the price, and then some other information. And then you can just go through and think about the different characteristics of the data. So this is just the sale description. So how it was sold. This is an interesting one. This is love and affection sale. I would never like my love and affection to be sold. This is a description of why the property was sold. Usually these are sold for $1. It's the lowest sale price you can list, which basically just means you're giving it to your child or family member or friend. So these are just some descriptions. I have a bunch of data wrangling here. This is not that important, so I'm just going to run it. But essentially what we're doing is we're looking for valid sales. We're sort of reformatting a few things. We're we're creating a price variable. The price originally was not strictly numeric, so I'm sort of forcing it to be a number. And then I'm creating an indicator variable for high summer. So this is just like, is it May through, what's this, August? And then I'm creating an indicator variable for this. And then all I'm doing here is just creating strings. So this is, using the year to create a year string and so on. And then the last thing I'm doing is just dropping the missing values. So when I run this, I get this thing. We're going to keep just these, these are the main variables. We have price, year, the month, and then whether we're in the summer. Okay, so the first thing we're going to do is just run an OLS baseline. So this is just, we're going to, we're going to predict price using these categorical variables. So this is just, I have categorical indicators for year. So I have a bunch of years in the data set. And then I have indicators for month. So this just tells us, like the average sales price relative to the intercept for these different values. So the first, we're essentially comparing a property in January of 2012 to everything else. So then we have a bunch of categorical variables. Each one has a coefficient, standard error, and so on. And what this does is give us the average as different from the intercept term. So here, you would read this as 2013. On average, houses are selling for $1,300 more than they were in 2012. And then here you can see February is a bad month. March is a good month. April is a very good month. And so on. So what this does is just give us the averages. So nice. The next thing I'm going to do is maybe simplify this model. So maybe we don't care so much about the specific months, but what we want to do is compare whether a property sold in the summer, so May through August, has a higher price than if it's not in high summer. And we still want to control for year. So we want to remove the specific effects of years. And what you can see is high summer has a higher property value. So this, if you'll remember scientific notation here, this is 2.2, and then we have, we're going to move the decimal place 4 places. So this is 2, 9, so it's 1, 2, 3, and then there's a 0. So this is what, like $29,000 more if you sell in the high summer, on average. Or should we say on mean? So this is like an average effect, right? So let's run the same 2 models, but with a median regression. So we're going to run the quantile regression. We're going to set tau equal to 0.5. And the way we run this is using, we're also going to use stats models formula. So this is just sort of the same sort of syntax that I think R, I'm not so familiar in R, but I think this is similar to how R runs regressions. We just give it a regression equation, and then it fits that. This is also how Stata runs it. So we're trying to predict price using a categorical variable for the year. So we want year fixed effects, and then we also want month fixed effects. We're using smf.quantreg, and then we're going to use a quantile of 0.5. So this is the 50th percentile, which corresponds with median. When I run this, the first thing you'll notice is that this takes a second. The reason this takes a second, unlike OLS, which just has to invert and multiply a few matrices together, what quantreg is doing is actually performing a numerical approximation. So it's doing all these background things that we did in the first part of the second half of the semester. So we're using numerical methods to perform these estimations. So nice. So we get this this list here, and this tells us the very similar things to our OLS model, except these are in terms of medians instead of means. You can see a lot of this corresponds nicely. The intercept is definitely higher in the OLS model than it is in the quantile regression. But generally, these numbers are going to correspond, although some of them don't. So this one was probably due to an outlier. So the difference, so like a really, really big house sold for a very high value in 2013, which is moving the mean in a way that it's not moving the median. So this is large, and this is negative. So you can go through these things. The next thing we'll do is just run the simpler model with the quantile regression. So just remember the high summer coefficient. So this is like roughly $30,000 extra. And then this is the quantile regression. So this is 1.7, but with 4 more zeros. So this is 1. So we have 1, 2, 3, 4. So what's that? 17,000. So the median is roughly $17,000 higher, $17,000 higher in the summer. Okay, so what I'm going to do is just run direct comparisons. So this is just some code to prepare like a comparative data set. So these are just using the estimates. I have my OLS estimate here. I have my median estimate here. So this is the mean, and this is the median. And then I'm just going to compare the month effects. So the average difference from January. And what I have here, this is just making all of those comparisons, and you can just go through and compare the different estimates. Another way of seeing this is with a figure. So I just have basically that data set but plotted. And what you can see is like roughly they correspond, but the mean, as you'd expect, is sort of more volatile. The upper and lower have more of an effect than it does in the median. So this is quite a bit smoother, the quantile regression. Okay, any questions here? So this is nice. We can make these kinds of estimates, particularly when we care or when we're concerned that there are outliers that are impacting our results. That's when you would turn to a quantile regression. I think a quantile regression is often not the first place to start. In fact, I've never started here. Yeah, using a quantile regression is, I think, somewhat less common. But it's a great tool to have in your tool belt. We can also perform, quantile regressions on different parts of the distribution. So maybe we're interested in the estimate for like the 90th quartile. We can sort of perform any estimate any quantile. So this is just, the only difference here is that I'm changing this from 0.5 to 0.9, which gives me the 90th percentile. When I run this, again, it runs for a very long time. I guess less in this case. And this gives you an estimate for where the 90th percentile estimate is for each one of these values. So I think this takes maybe a second to internalize what this is doing. The 50th percentile gave us sort of a comparative to the mean that we get from OLS. This is just not at all like OLS. This is giving us an estimate of the 90th percentile, which is not a measure of the middle point of the data. This is giving us an estimate for the 90th percentile. Okay, any questions there? And then we can do the same thing here with the 99th percentile. And here I'm getting an estimate for high summer. Okay, so this is really nice. We can do a lot of things. This is a picture I made to compare the 90th percentile to the mean and the median. So we have the median in yellow, we have the mean in blue. And what you can see is when we're estimating the 90th percentile, we're getting much more extreme values, right? We're closer to the extremes, and so the extreme values are going to move our estimates by more. It looks maybe like the summer is more important if you're buying a very expensive house, which is interesting. But because we have less data, this may be more due to outliers. Yeah, so it could be because luxury buyers are more selective with timing, but it may just be because there's less data. Okay. So nice. So we can go through and do a bunch of comparisons between these different models. So if you run this, it's just going to go through and estimate different quantiles. The first one is going to just be OLS. So this is the effective summer for the mean. And then as this runs, it's going to get different quantiles. So this is for the 10th percentile. Here we're getting that the effect, like prices are higher in summer for the 10th percentile by around $10,000. And then we're just going to run these through. And as you'd expect, these values are going to increase. So the impact of selling, or let me say this differently. The sale price in the summer across these different quantiles is going to be higher as we move into the more luxury market. Sort of almost exactly as you'd expect. Okay, so as you can see, this is a very flexible approach. Is useful for certain kinds of things, but I want to spend a second just talking about interpretation. So think about this first question. Suppose you run a median regression on wages, of wages on years of education, and get this number. What does this mean? So we have a beta 1 hat of 5,000. Our standard interpretation is something like this. So with OLS, we would say something sort of like this, right? Every one additional year of education gives us $5,000 more in earnings. Right, that's what the beta 1 estimate is doing in OLS. With quantile regression, this is ever so slightly different. In this case, what the beta 1 estimate is doing is it's saying that the median wage among people with X plus 1 years of education is more is $5,000 more than the median wage among people with X years of education. So it's sort of like we're moving up the distribution by one. We're thinking sort of in sort of conditional quantile effects. This is pretty subtle, but the main idea is essentially that you're comparing like different groups, right? By looking at different estimates, we're comparing different groups and not thinking about a single person. The bigger idea is that we don't have this law of iterated quantiles, right? Like when we're thinking about law of iterated expectations, we can just take an expectation operator on the conditional, and that gives us the expectation of y. But for quantiles, we don't have this. The closest thing we have is this, that the beta 1 is equal to the sort of movement in the median with respect to years of education, given some level of education. Okay, so this is the sort of main distinction here, that we're dealing in medians, and those medians are like the sort of calculus that we typically think about when we take expectations of these things. We use them for interpreting our betas, and some of that sort of breaks down when we're dealing with quantiles. Okay. There's a little bit more here, and we could run a little simulation, but I think there's not a whole lot of extra, additional insight to be had here. I only include this for sort of additional study, if you like. But the last thing before we take a break, I just want to leave you with what we've done and how it all sort of connects together. Nonlinear least squares and quantile regression basically share a similar structure. One, we're relaxing the assumption of the linearity, but we're targeting the conditional mean. So we look at some point on the horizontal distribution, and we're making a claim about the average at that point. That's what both OLS and nonlinear least squares do for us. Nonlinear least squares is just relaxing the assumption of linearity in the parameters. Quantile regression is doing something parallel but different. We're going to have a linear loss function, so just like OLS, but we're going to think about the conditional quantile. So this is, we're making an estimate of the quantile directly. So instead of interpreting our betas as increases in the horizontal axis, all we're doing is making an estimate of the average, or the percentile at that tau. To get differences, we have to then compute differences in the quartile. I keep saying quartile, I mean quantile. Okay, so if you want, you can then go through, we've already done some of this, but you can go through and compute a few more things. Okay, any questions here? All right, so where are we at? Are we at 13-minute break? I think today's a 13-minute break. Titrating down. So let's come back at 10:29. Stick around if you have questions. I'm going to be drinking some water. We're going to talk about maximum likelihood.